Hey folks, we want to go a little farther in this rabbit hole we got here. I'm going to start talking about electricity, obviously there's electrical circuits, and get into a little bit more about Ohm's law. So without further ado, let's go ahead and share this with you. All right, here we go. And go ahead and get it up and running. All right, so when we talk about electrical circuits, we're talking about a completed type circuit, and we'll get into a little more about that. But there's definitely, and like I said earlier in the last video, if you get the basics down, you're going to do really well. I would encourage you to replay the videos to kind of help yourself out, because this will definitely piggyback on other systems as you go along. Remember, this is kind of an introductory semester class, and we'll get deeper into it and give you some electrical projects when you get into the Auto 116 class, which is our electrical class. And then you can progress on to the Auto 216. So please look forward to that. So our objectives, of course, is to identify the different parts of a completed circuit. We're going to talk about describing the characteristics of different types of circuit faults. We'll also get into explain Ohm's law as it applies to automotive circuits. And then we're going to talk more about Watt's law, okay, as it applies to the automotive circuits like that too. So circuits, the definition of a circuit, circuit is a complete path that the electrons travel on the from a power source. So in the last we showed that completed circuit. I'll show you a picture of one just in a few minutes. For any electrical circuit to work at all, it must be continuous from the battery power going back to the battery ground. A circuit that is continuous throughout is said to have continuity. Okay, so it makes contact, we'll put it that way. So here's a completed circuit. You'll notice on this circuit, I have a battery right here, and this is going to be my source of energy. It will have a start. If you look at the electron flow, it goes through a protection device. We'll get more into the fuses and protection devices we go across. And then has a bulb, which is doing work for us. Turn on that bulb, our load, and then it goes all the way back to the finish line, let's put it that way, and it goes back to the negative like that. So we have a power source, we have a protection device, and we have a path to go. So these wires here are our path, to actually make a completed circuit or make sure it's continuity is involved. We can have a circuit that is all completed like I just showed you on wires, but a lot of times what we do to keep the wiring looms down, keep down the amount of wires, is we do different paths. We can actually use a metal body. The frame on the car can actually be part of a ground circuit. So we don't have to have a completed wire going across. We can actually ground it here and put the other ground here, and it will find its way back to home. Okay, we have this one again showing pretty much the same. We've added in a switch this time. Okay, I would prefer to have some kind of protection device too. And one of the things we look for in the automotive field is looking for open circuits. This is where it didn't have a completed path. You got something that doesn't turn on. That light bulb doesn't turn on. Is it a bad bulb, or is it something else? So we can have like broken wires. We can have a part that's internally short, I shouldn't say shorted, open, okay? And then that's short is another thing. We can have a blown fuse because it took too much, it actually, not resistance, well, it could be resistance, but it took too much current and it hated that fuse and melted it. Or we could have a corroded connection to it. We can actually have loose connections too. So all the connections need to be tight and they need to be clean. And this is how we start looking for faults. So another fault, type of fault, is a short to voltage. It didn't go through the load. It actually went across the load. And, I've seen some things like somebody inadvertently put a screw through a frame, I should say frame, but through a part, and it made connection between two voltage. And now we have a fuse in place, and we actually doesn't show, but that load would not even come on. In other words, if that was a light bulb, it wouldn't even glow. And if it goes across like this, you wouldn't know it, because this little fuse would blow. In other words, it would open up and then you would have an open circuit. So sometimes when you have a fuse, and which is a good practice, if you have a fuse that actually opens up or blows, you want to see what caused that to do it. It's not just throw a fuse in and let it go. You may have something that's causing to blow that fuse. And don't go please do not continue to add heavier fuses, because that's not going to help it out a lot, because eventually if you get too much going, you can actually cause a wire fire. Other circuit problems, and this is where you can blow a fuse right away, is if it has a short to ground. And this is where I've seen more. So people put in their own speakers, they'll mount something up, and they didn't look to where the wires were. So what it'll do is, instead of going through the ground path to through the bulb, it will actually go straight to ground, and that causes no resistance. And now when they turn on the switch, it'll blow that fuse right away. Excuse me. So other things can be a problem with our actual conductors and stuff like that, is we have to take in consideration when we design a circuit, and this is where the manufacturers do painstakingly time on it. You look at their wire lengths, because wire lengths will cause more resistance. Sizes of wire can cause more resistance too. Instead of having this big area to actually have the electrons go flow across, now you put something smaller, can actually cause heat, and you can actually cause fires too. If you have, like I said, the thickness of it, if you have the temperatures, as the temperature rises, resistance changes, and that can cause an issue also. So there's different things that can actually cause faults, and you got to kind of look around at the whole thing as you go across. Now, I gave a brief part about Ohm's law in my last video, but let's get a little bit further. It was George Simon Ohms that actually established the actual laws on Ohm's law. And electrical, of course, we know that the electrical, or the voltage, is actually the pressure. And that's what we got into, just a little recap. And then resistance is in ohms. And then the amount of current flow is actually measured in amperage. So Ohm's law, which is really, this is where you kind of go, oh gosh, math. Oh, I don't want to do this math stuff. but it's not as hard as it seems. And especially if you got your phone, you can actually calculate it out real quick. Now, I do want to put a little caution into this. This is what is expected. What I mean by that is when you start calculating it, this is what's expected. And we do a lot of what's expected when we build up some of our different measurements. So if we look at how much we expect to be in the resistance, how much we're building a circuit. So we need to know we have this voltage and this amperage, and then we want, and with the completed circuit, we know we need this resistance. Okay, we can figure out the resistance of that bulb. We don't know what the resistance on that bulb is. So if I do my calculations, I can find out what the resistance of that bulb is. Should be. This is my expected. Okay, we use a lot on figuring out different faults. Let's put it up. We should have almost zero resistance at a ground. Okay, we should have close to zero resistance in a completed circuit to make that circuit work correctly. So we use Ohm's law to do those calculations. So if we want to do the calculation, we do want to do the calculation. So notice I said that some of these equations put on different letters. So and we would normally say V instead of I. So I is for the actually the voltage, and or we can actually put it as E. Okay, so E is I over R. Okay, so my intensity or my amperage, okay, is I, and then my electromagnetic force is E, sometimes is V, which gets a little confusing, but stay with me here. And then resistance, we normally do an omega symbol on it. So depending on how you're calculating, whether it be you're doing it to design something, if you're an engineer, you're going to use the IER, but a lot of times you'll see in the automotive field we do the A, and then we do voltage, and then we do mega symbol. So just put replace it with what you feel more comfortable with, as I'm saying. But when you get into tests and so like, kind of keep that in the back of your mind too. All right, so I equals E over R. So if I want to know what the voltage is, of course, I'm going to actually cover up the voltage, and I'm going to multiply the actual amperage by the actual resistance, and that's going to give me my actual battery. Okay, or my voltage. Let's put it that way. So if I want to know my my actual resistance, and I divide the I by the E, and you kind of get the flow of things. So if I want to know the actual amperage, and I'm going to divide the R by the E. So I kind of go the E time by the R. You kind of get the flow of things like that. So here I have my my little 12-volt battery. So if I take my 12 volts, and I can figure out my amperage by dividing that 12 volts by the 4 ohms. Okay, so I've got 4 ohms right here, and I've got a set of wires going across. Okay, I know this is 12 volts. But I want to see how much amperage is kind of going across here. So I can take that 4, divide it into 12 volts, and it gives me my amperage, which is going to be 3. Okay, pretty simple in a way. All right, so Watt's law, this is where we do by power. So your actual motors, a lot of your electrical parts are measured as actually rated in watts. And how we do that is we take, and I'm going to give you have a little wheel up there, and I actually put it in your reading too, so you'll have that to go with this lecture too. And so, of course, Watt, he actually was a Scottish inventor. He first determined the power of a typical horse, which measures the amount of coal being lifted out of the actual mine. So how much power that took for that horse to pull that coal out. So electricity can also be expressed in a unit of power called a watt. And the relationship is known as Watt's law, which states 1 watt is a unit of electrical power represented by a current of 1 amperes through a circuit with a potential difference of 1 volt. So the formula, okay, the symbol of the watt is the capital letter W. The formula for Watt's law is the actual wattage equals the amperage times the voltage. Another way to kind of can express that, because a lot of times we do it in P, is, the letter P is P equals, instead of W, P equals the amperage times the voltage, whichever is easier for you to remember. But remember, okay, that if for the quizzes and stuff like that, we're going to be going back to what the book says. So here is the little magic circle, you might say. The formula for calculating any combination of electric units is shown. Okay, it is almost impossible to remember all the actual formulas. So this one circle showing all of the formulas is nice to have available if needed. So if I do any kind of quizzes, I'm not going to just throw you out, figure out what's law. You should know it. It's pretty simple, but for you that might not, you can actually go ahead and figure out what the actual wheel. Okay, so this is all I have for right now. Let's do a little recap on it. So all completed electrical circuits have a power source, such as a battery, a circuit protection device, such as a fuse. We'll get more protection devices as we go along. A power side wire or path, and an electrical load, and a ground path back, and a switch or an actual control device. We use a lot of computers to control a lot of it now. A short to voltage involves a copper to copper. A short to ground involves a path going directly to ground. And open is a break in the circuit. Ohm's law states that it requires 1 volt to push 1 ampere, okay, through 1 ohm of resistance. And then Watt's law states that a watt is a unit of electrical power represented by a current of 1 amperes through a current, a circuit with a potential difference of 1 volt. So that is it for now, folks. I'm going to go ahead and turn off the PowerPoint. If you have any questions, please feel free to reach out to me. Anyways, I will talk to you in the next video. Take care now. Bye for now.